All right, so moving on to 17.11, the magnetic field of a bar magnet. So this is probably what you think of when you think of magnets. If any of you have been ahead in the labs, you've already played around with some bar magnets, and I'm going to illuminate you with something shocking. Magnets have magnetic fields. I know. I know. I just blow your minds every day. All right, so now obviously this is something that you've known since you first played with magnets. You had some sense of their field, but let's look at how to dissect this a little bit more. So if you think about your playing with magnets, you know that they have a north end and a south end. And we would know that if we were to put another magnet here, they would be very attracted to each other. So you would see attraction here. If you were to line up two souths together, they would be repelling each other. They want nothing to do with each other. Yuck. So just like with charges, opposites attract. And like repels. Also, just like with electric fields, you have a superposition principle. It still works. You sum all the magnetic field contribution in one location to get the net magnetic field. Now, there are some differences between electric fields and magnetic fields. So, and again, these are things that you've probably observed by just playing with magnets. So, electric fields impact everything. I mean, you had tape sticking to your hands on the non-sticky side. But a bar magnet interacts with iron or steel objects. Not everything is magnetic. Whereas charged objects interact with everything. And we've seen that charged objects will lose charge. Magnetic objects tend to keep their magnetism. Now, if you take a magnet and drop it over and over and over and over again, you will eventually demagnetize it. Please don't drop my magnets. Actually, the magnets we have in this lab have been dropped many, many times. I can tell I need to get new ones, one thing at a time. But the point is, they keep their magnetism a lot longer than a charged object will keep its charge. And then one thing, magnets have curly fields. So when we talked about the magnetic field around a wire, it's curling around. Curly field. All right, so a bar magnet is a magnetic dipole. And it has a field actually pretty similar to that of an electrical dipole. So with the north, this is the one that goes away, south points in, and then you'd have something like that. But it would be not similar towards negatively, positively charged, where you'd have pointing in and then pointing out. So, and also this is a field similar to a current loop. All right, so let's do an example. We have a bar magnet with a mass 56.4 grams. So we're lining it up. So Earth north is in this direction. The magnetic field of the magnet would go here, and then on our compass we see a 7.2 degree deflection. Oh, 72 deflection, not 7.2. And we want to know what is the mu of the magnet. So in this case, B net is going to be the magnetic field from the Earth plus the magnetic field of the magnet. So B mag is equal to B Earth tan of 62 degrees equals 2 times 10 to the minus 5 Tesla. Tangent of of 72 degrees, which is equal to 6.16 times 10 to the minus 5 Tesla. And B mag is equal to mu naught over 4 pi 2 mu over r cubed. And so mu is equal to B r cubed over 2 mu naught over 4 pi is equal to 6.16 times 10 to the minus 5 Tesla, 0.22 cubed over 2 times 1 times 10 to the minus 7 Tesla meters over. So mu is equal to 3.28 amp meters squared. And we're going to hang on to this because this is going to come back in a different example. All right, so the magnetic field of the Earth. So we have a magnetic field. That we've been talking about. And it looks like a dipole. It has to do with our molten core in the center. Our magnetic field looks like this. So you will notice we have a type S at the North Pole, and we have a type N at the South. Again, just one of those things where we've come up with certain conventions and then we learn more and we realize the conventions were a little bit wrong. So North is still up, but we have presently a type S magnet at the top. Of course, the poles have switched several times throughout history, so and we're due for another switch, and there's some, our magnetic North Pole is moving, but it will take hundreds of years in order to switch. So if it is actually going towards a flip. So a compass points towards the horizontal component. of Earth's field. So, and by the way, the magnetic field strength varies a little bit. So, in Maine, the magnetic field of the Earth is about 1.5 times 10 to the minus 5 Tesla. And most of the U.S., it's 2 times 10 to the minus 5 Tesla. And Florida and Hawaii, it's about 3 times 10 to the minus 5 Tesla. Just to give you an idea of sort of the differences between the magnetic field strength depending on where you are on the planet. Okay, so moving on. Now, with charges, you noticed that we started with something called a point charge, which would be the simplest version. I did not talk about point magnets, and that's because there are no magnetic monopoles. If you cut a magnet in half, you get 2 magnets. With 2 poles, which is far, far different than charges. So the field of a point charge, which looks like this for a magnetic field, does not exist. Never been observed. Well, as far as we know, it doesn't exist. And we're pretty sure at this point it probably truly doesn't exist. Although, if you do an electromagnetism class, you will do Maxwell's equations with magnetic monopoles, and they do work out, which is something that's interesting. So there are a couple theoretical physics researchers who do think that the magnetic monopole does exist, and there are physics models that work with the monopole. So just something to think about, or something just to pique your curiosity.